Um, Hello, everyone. My name is Aziz Murtazaev. I'm a software engineer at Facebook, and I work on Litha, open source UI framework, and also I work on related tools. And from the starting from last year, we started investing in benchmarks, and we would like to share what we have learned and some tips and why we need this. And so in this year's Google I/O, Google announced Jetpack benchmarks. So how many of you have watched or tried benchmarks, Jetpack benchmarks? Okay, I can see a few hands. That's already quite encouraging. Today in this talk, I am going to cover first why the why part of the benchmark, why we need this, and then we will go through how we do benchmarks, and then benchmarks at Facebook, and then I'll talk about some tips or gotchas in the end. So yeah, let's start with, before diving into benchmark details, let's go through the story of app testing. So let's say you are a developer, sole developer that's building some app. So the app is pretty simple, and now the question is how would you test the app? So when you're a sole developer, it's you can do it manually, and as you control all the parts, and then you start adding more developers, and you add more features to your app, and then you can kind of stepping in each other's toe, and manual testing won't be that much convenient anymore. So you start investing in unit tests, integration tests. So you can use tools like JUnit, Roboelectric, or Espresso, and you can run these tests from time to time. Then you start adding more developers, and your app gets more popular, and you add more features to your app. And you slowly start realizing that running from time to time is not great either. In between time when you run tests in previous time and this time, there might be some breakages, and you will be going back and fixing all this, and then naturally you will come to the next step, which is investing in continuous integration tools. So now every pull request that goes through continuous integration and makes sure that it doesn't break anything. So now we have some sort of safety mechanism. But your app keeps evolving. You add more developers, and they are adding even more features. So now you have, because of continuous integration, everything is green. So you're happy, right? When your app gets big and complex, it starts getting slower and jankier. And if you look at the tests, everything is good. However, the standard tests shows only correctness. So it has it either passes or fails. So it's kind of binary result. However, the qualitative aspects of the app is not covered by standard tests. So what could be qualitative aspects of the app? So you can think of how fast your network, you can get the data from network, or how compressed your images is, or or like how efficient is your UI rendering. So we will be focusing on UI rendering part because that will be a significant part of the user's perception of app quality. So let's talk about the performance of UI performance. So how fast or slow your app UI renders affected by like affects like startup time, screen transition time, or scroll performance. And if your app like starts in like 2-3 seconds, it's not great. And especially if you have like utility app when users just like want to go to your app and check something and then leave the app. If it loads in like 3 seconds, maybe eventually users start like leaving the app. Or like screen transition from like you're moving from one surface to another surface, like, and it should be also like fast as possible. And also like a scrolling performance. If it's like stutters, it's not great experience either. So overall, all these factors eventually affects the user engagement. And your install rates might go down, and people might even start uninstalling apps. So let's dig a bit deeper into how UI rendering works. It's kind of quick recap. So most of modern devices can render 60 frames per second. Well, there are some few new ones that can render more, like 90 or 120, but for the sake of this presentation, let's discuss the 61 because that's the most common. So 60 frames per second means that in each frame you have around 17 milliseconds to render single frame. And single frame consists of those operations like processing input, processing animation, processing, like doing measure and layout, and then finally drawing it. All of this need to happen within 16 milliseconds. If we skip the input and animation, because in most critical interactions, they don't happen that frequently. We can see that measure, layout, draw are like the central part of like UI rendering. When these operations takes a lot of time, the time it takes to complete the one frame goes beyond that line. So it doesn't fit into a single frame, and user experience like frame drops or so-called jank. So what contributes to this? There are a lot of parts where which app developer controls that affects frame drops. Like how your view tree is structured, like how deep is your tree, or like how do you do binding and some other app level code. Okay, so you found a problem, and how do you debug these kind of problems? Let's look at the ways to debug these kind of issues. So one of the options is the one that's available in developer options. So it's called GPU overdraw. It identifies extra drawn areas like this. So how many of you have used or use GPU overdraw? Cool. I can see quite a few hands. So basically, it shows the color-coded parts of your screen, how much each pixel is being redrawn. So blue means that it's redrawn one time, green is like 2 times, and it goes up to like a red. And so yeah, we need to fix header here. So another tool that's available also from the developer options is called Profile GPU Rendering. Basically, it shows in real time like how your UI is being rendered by showing bars. So I'm not sure you can see there is a green horizontal line that shows the line of like 16 milliseconds. Whatever goes above results in like a frame drops. So you can like scroll and move from one screen to another screen, or like do start new app, and you can see how much like you are going above this line. So when you identify these kind of issues, you can like start working on it and like fix it, and then look it again and like iterate on it. Or you can use the command line tools like ADB Dumpsys. Graphics Info provides you some information about how many frames were rendered, how many janky frames, and like slow commands, slow draw commands, and so on. Or you can go even deeper. So how many of you use systrace in daily work? Okay, nice. It's pretty cool. So systrace is a very powerful tool. So it gives you very detailed information about what's actually happening in the app. It gives you information about each process and each thread in the process, and some instrumented code. Also, you can see like CPU information, what each CPU core is doing. And you can even identify like race conditions, like which thread is using which lock, and so on. So you have a lot of tools to identify the issues and trying to fix the rendering performance issues. However, this is still manual process. So even though you fix it, when you have a lot of developers, you'll like go back to square one, and it gets worse again, and you fix it again, and it gets worse again. So is there any sustainable and automatic way to track performance and avoid regressions? So we'll be talking about benchmarks. So for the purpose of this talk, we can define benchmarking as measuring performance of code execution and comparing the results with the same execution over time. Here we are mostly interested in UI performance, and using benchmarks we can automate and compare to historical values. So let's look at the example before diving deep into like how we can write benchmarks. So example can also give some sort of mental model how this works. So let's say you have this kind of screen. First question to ask yourself is like, which part of the screen you want to benchmark? So the rule of thumb is here is like any part of the screen that's repeats frequently and can be good candidate for benchmarking. So in this case, like every newsfeed story has header, and we can use that header for the doing benchmarks. So what we can do is like a measure rendering time regularly, continuously. What it incorporates, basically we measure like how long it takes to create UI elements, binding data, and doing layout. So let's look at the, for example, your master branch. You have some, the current head is at, let's say, 37, commit number 37, and the rendering time for the header took like 10 milliseconds. And after some time, you do a measurement again, let's say at commit number 43. and it took 14 milliseconds. And now we detected regression. So the rendering time increased by 40%. And because this is like such a frequent component, it will affect, yeah, even though 4 milliseconds might seem not a very big deal, but if you are rendering that component many, many times, and also it has, it's being part of each individual like a story, like newsfeed story, it will affect the total like a UI performance significantly. So we found that, yep, sorry. So we found that the rendering time increased from 10 to 14 milliseconds, and there are a lot of commits between two measurements. So we don't yet know which commit caused the regression. What we can do to find the culprit, or like the commit that caused the regression, we can do bisect. We know that the blame commit is between these commits, and we do bisects, and we measure those individual commits. So number 40, it's 10 milliseconds, so the regression is on the right side. 42, it's 14 milliseconds, it's on the left side. And we do the same for 41, and then we finally found that the commit the commit number 41 is increasing the rendering time. So now we found the blame commit, sorry. So we can either revert it, or if this was unintended change, or maybe accept it if this was expected overhead, some new functionality that uses some computation. So let's look at how we write benchmark tests. So we use custom test runner. We call it UI test runner. It just extends a block JUnit for class runner. That's the default one when you run JUnit tests. And for each test method, we annotate it with @benchmarkTest. And the test method returns UI test case. So you already might notice that this is quite different from standard JUnit tests. Standard JUnit tests, you don't return anything. Like you do assertions inside your test methods. However, we are capturing the UI test case. So what is UI test case? UI test case is an encapsulation of your UI element, and also it captures like how you can create view, how you can bind, and dimensions. So we have the view test case. It has a lambda it accepts lambda function that, given context, can create your tree or your view, or like a tree of views. And then you have a bind view. It's also a lambda function that can bind your inflated or constructed view into whatever data that you provided. And then there are like dimensions. So basically, this is capturing information about how your view is structured and how it's bound. So we are not yet testing anything here. It's just like all the meaty part is happening inside the test runner itself. First, let's look at how, if we run this benchmark, what would the output look like? So we run benchmark, like provides the class name and it will produce like for each test method, we produce like multiple metrics. So for example, how long it took to create a view. So we had the lambda, we can like measure that. How long it took a bind view, and how long it took to calculate the layout of the view. So how do we actually do that internally? So in JUnit, every test method is processed by a class called a framework method, which has this method called invoke explosively. And you just invoke the test method that's provided. And we extended that. And then what we can do is, like, first we get the, we call invoke. And unlike the other JUnit tests, we are not doing assertions or any checks here. We are getting the object, like the test case. And so we have the metrics that I just mentioned, like create view, bind view, or like layout view. And for each metric, we do like a first run, which is perform benchmark and pass the test case. This is for warm-up. Why we need warm-up? Because we might use some singletons or any objects that need to be, that might take different time depending if you are running first time or not first time. So we need to warm up those caches or like initialize all these singletons. Then we save the start time, and then we do iterate and call benchmark, perform benchmark many times. So you can either fix the iterations by like a fixed number or by some timeout. So it's very hard to know like what is the good number to iterate. So you might have some sort of like a minimum number of times, or like a minimum time to run the benchmark. So you can like check the current time. And then you save the end time and you report the result. So here you have information about how long it took overall and like how many iterations you did, and you can calculate like averages. And that way this result is aggregated to the overall result. So let's look at the one example of metric. So we called metric for like create view, bind view, and layout view. So let's look at the layout view. So it has the method called perform benchmark. It accepts test case. What we do is first we get the measure specs of, because we already in test case provided like width and height. Then we initialize views. Then we do binding. And now we can do measure and then lay out the views. And however, we are interested only in the measure and layout part. So the previous like setup part should be excluded from the benchmarking time. So how can we do that? We have this suspend and resume static methods, which will exclude this specific part from the total calculation. Okay, so this is how we do the benchmarks for views. So let me talk about benchmarking declarative UI code. So declarative UI frameworks like Litho makes it really easy to separate UI rendering code from the rest of the app code. So it's it has a unidirectional flow of programming model where you have immutable data and you pass it to component function, and it it always returns the same result. Which means that this is very good candidate for, so this is like a, it can be measured in isolation and it has no side effects. Unlike views, which has the internal state and anyone can change anywhere. It can be compared with historical values and it's really good fit for benchmarks. So for the, by the way, how many of you have tried litho? Okay, not many, but okay. So let's look at how the test class would look like in case of litho. So this is the previous example with views. So you have the view test case, lambda for creating view, and lambda for binding view. And when you replace with litho components, it will be just one lambda, which is like the way to the rendering function of the litho code. So when we run the benchmarks, the output would be similar, but instead of like obviously create bind layout, we have different lifecycle methods of litho, which is like create component, layout component, mount, unmount. So mount in litho means actually like adding those drawables and views to the view tree. So how we do benchmarks at Facebook. Most of the screens in Facebook app is rendered by litho, and we choose a selected number of components to benchmark. So how do we choose? So we frequently render components that affect like a scroll performance are a good candidate for doing benchmarks. Also like components that load a startup like a newsfeed stories can be also good candidate for doing benchmarks. So most of benchmarks we run it regularly in our CI system. I'll talk about it a little bit in a bit. We run it like once in 1 or 2 hours, depending on load. And whenever we find a regression, well, whenever the system finds a regression, a task is automatically created, and it's bisected to the commit, blame commit, and the task is assigned to the author of that commit. There is another way of using benchmarks. So this one, the previous one, is more like a reactive approach, where you submit some code and then the system tells you, hey, there is some regression in this code. Or like some teams can proactively like optimize their layout and or some optimize opcode and then verify in benchmarks locally that they have some rendering wins. However, they still need to verify the changes in production, like with A/B testing. So let me talk about mobile lab. So we have data in our data centers. We have a fleet of physical devices, like Android devices, and we run all sorts of tests there. And we run for the benchmarks. We use those devices, and this is the flow. How step by how the mobile lab manages, well, how mobile lab does the benchmarks. So first you check out repo, build test app, and then you get handle to real device in data center, install test APK, run tests in many iterations, and report results to experiment store, and then you can bisect if you need it. The results of the mobile lab, we have a dashboard that looks like this. This is for individual component for single metric. So this is the layout component. So different colors means different app versions, and you can see that the black line was like two lines were kind of overlapping, and at some point the darker line goes up. This is where the regression happened, and you can see the one on the one in the above is the current master, and the one below is the last release commit. So whenever something changes, we know that compared to last release, something has regressed. Or we can also find like improvements. So here also you can see different colors, and in the black one, after some point, the darker line went down, which means that we are now rendering the mount component metric went down by around millisecond, more than millisecond. So yeah. So benchmarking is hard. There are a lot of problems with benchmarks. First is like the execution environment consistency. So what do I mean by that? The CPU frequency, disk throughput, and memory network, they don't produce like they're not always consistent, which means that, for example, let's take CPU. When your battery level goes down, the Android OS automatically lowers down your frequency, CPU frequency, or like your device heats up, then it goes down, or like some other background operations going on and you don't get enough frequency. So if like we run the tests and it would be very hard to get like a consistent result. So same with disk, like disk I/O might vary quite widely, and same with memory and network. Another problem is like code path consistency. So you need to run the same code path again and again, and it should be produce consistent results. So how do we solve them? So for the first one, for the execution environment, we use real device, not emulator, because emulator is not representative of real behavior. Then we lock CPU frequency. So for the reasons that I mentioned before, like CPU frequency might vary quite widely. So for that, you need to have like a locked device, but we control the devices, so we can do, the device should be rooted. So because we control all the devices, we can do custom setup on the devices. Then we mount the disk into RAM, so we don't have the issues with like a paging or like a in-memory cache access when you're accessing disk. And for network requests, we can set up some proxy so that it always gives at the same the network results at same time. For the code path consistency, to have like a consistent way of having stable results is like you run the same code like many times, repeat multiple trials, and then you can exclude like outliers and get average, like and so on. And let's talk about like gotchas of benchmarking. So absolute values in benchmarking doesn't mean anything. It only makes sense when you compare that number with similar run in the similar environment, because this is not actually a production environment. It's more like synthetic environment because of those like a CPU locking and the mounting to disk to RAM. It won't be exactly as in production. So so the mobile lab tries to be directionally correct. So when something moves up, it's highly likely that it also will move up in production. Running benchmark is not cheap because first we use real devices, then compared to regular instrumentation tests, which runs only once per each test, benchmark runs each test like multiple trials, multiple iterations, and multiple trials. So that's why it's important to select the representative ones that will be mostly affecting the rendering performance. Also, benchmarking cannot fully replace analyzing the perf data from production. It's more like a complementary. Another problem is like noisiness. So if benchmarking results are producing a lot of noise, then it's not really useful. So it's important to make sure that keeping track of like a noisiness of metrics, and if it's very noisy, try to figure out like what's actually causing the noisiness. And the build type of the app should be the release version of the app should be used, because in the release version of the app, you might do some optimizations like ProGuard or some other steps that makes it very different from the debug build. So yeah, that's it. We have 3 minutes, I think. Do you have any questions?